Okay, hello everyone. I'm going to talk to you about CMB spectral distortions and the kind of science that we can do with these signals. And in particular, I want to highlight some of the synergistic opportunities that we have with CMB spectral distortions. I'm going to switch off my video because it's just going to be distracting me, and I think it will also cover some of the slides. So let me just immediately get rid of that. Okay, so starting with CMB spectral distortions, one of the important things to do is to contrast it to the microwave background anisotropies. So we have all heard about the microwave background anisotropies, and I'm sure there's many contributions that are highlighting all the extremely interesting things that we have learned from these anisotropies. But for my talk, I'm going to totally forget about this. For me, the average sky signal is what's important, which looks like this. It's just the monopole of the microwave background. And we are learning basically from the energy distribution of this signal. So this energy distribution has been shown to be that of a black body to extremely high precision by Kobe-Firas in the 1980s, 90s. And we know that the temperature of the microwave background is close to 2.7 Kelvin. With these departures from the black body shape, which are the so-called spectral distortions, which I'm going to talk about in more detail, being limited to very, very small amounts. So this is, if you will, one of the most perfect black bodies in the universe that we can have, and it is really something that was created from the early phases of the Big Bang. Okay, so why would one even expect spectral distortions? Because that's, of course, one of the big questions to ask. And if you're just thinking of a photon fluid being in the universe and expanding, then that wouldn't be changing really the spectrum of the energy of the photons. You would be determining everything with one single parameter, namely the temperature of the photon field, and then number density, energy density are given. This is not exactly correct because we have the baryons that are coupled to the photons that continuously actually extract energy from the photons, since they have a different adiabatic index and want to expand, cool down a bit faster than photons would be cooling. And that means you actually get negative energy release, so cooling of the photon field, which leads to a negative chemical potential. I will come to that a bit later. Okay, but if you have something that disturbs the equilibrium between matter and radiation, like energy injection or photon production or injection, then you will momentarily distort the microwave background spectrum. And then the big question is basically, will you have enough time to restore full equilibrium by the processes at work after the Big Bang? The most important ones relevant to the thermalization of spectral distortions are Comptonization, double Compton, and Bremsstrahlung, and that all in a homogeneous expanding background. So this picture immediately tells you that when you look at spectral distortions, you're actually learning about the thermal history of the universe, so energy release processes and things that perturb your equilibrium. So the classical distortions are the so-called Y-type and mu-type distortions. I mentioned the limits already from Kobe-Firas a second ago. And these distortion shapes, they have been discussed for many years. The Y-type distortion is really the equivalent of the Sunyaev-Seldovich effect, but here now coming from the high redshift universe, where you imagine that you have energy transfer from the photons, from the electrons to the photons, and you're in the regime where you're only transferring very, very weakly the energy. So you're interacting very weakly, and you're just basically moving the black body, the initial black body field, slightly upwards and producing, this distorted spectrum. So this distortion is in the inefficient scattering regime, and it would be relevant at low redshifts, which for me is redshift 50,000 or so. Of course, those people that are thinking about early universe physics, this is not even that lower redshift for people that are looking at galaxies, for example. And then in the other extreme, when you have very rapid comptonization, you get the so-called chemical potential type distortion. Here, the solid, thick black line, where you have, again, a deficit of photons in the low frequency part. And then you can see that it's going above the curve A, which is the black body spectrum. So you have an increment at high frequencies. But this is a distortion that is only created when you have very rapid interactions and the possibility basically to exchange energy across the full microwave background spectrum. This is a distortion that is guaranteed to come from the early universe. If you see a mu-type distortion, you know that this is a signal from the early phases of the universe. So these are the classical pictures that one looks at, but there is the representation in terms of like the real difference to the microwave background. So this is just highlighting the different key spectral shapes as a function of frequencies. So imagine you have an injection of some energy at some redshift of 300,000, then you would get the distortion that you would get, it would be this blue line, where, as I already said, you have a deficit of photons with respect to the black body at low frequencies, and then an increment of photons at high frequencies with a crossover frequency around 130 gigahertz, in fact. This is the mu-type distortion, and the y-type distortion is the black line. Which is, as I said, the equivalent of a high redshift Salyers-Selldrich effect with a crossover frequency at 217 gigahertz. And then this red curve is just the full thermalization curve. If you started with a black body of lower temperature and injected some energy at a redshift of a few million or so, you would create a black body spectrum again and just restore, basically shift the black body from one temperature to the other. Okay, so let's put this into context. Here is a history of the universe, a sketch of the history of the universe that we have all seen. We start with the Big Bang, and then inflation occurs, as we believe, blowing up these small quantum fluctuations to macroscopic scales. And then as the universe cools down, it goes through multiple phases of, particle creation and BBN and all these things. And then it enters here into the recombination era at around 400,000 years after the Big Bang. This is when we are starting to be able to see really the anisotropies in the microwave background that then more or less freely propagate towards us to be mapped with Planck and other experiments. And then at low redshifts, we have all the fun things happening with galaxy formation and structure formation, which is, of course, a highly complicated process. So this is what we usually think of when we think about CMB anisotropies, where we study, as I said, these signals from the last scattering surface, and we have all these other additional processes at low redshifts leading to additional signals. But the goal is, of course, to learn about the initial conditions of the universe. With spectral distortions, we're able to look into the pre-recombination era because we can actually test the energy release that could be happening there. And I'm drawing here this box, basically starting at a couple of months after the Big Bang until today. So if we have energy release or any perturbation coming from a photon injection or things like that, we would get a spectral distortion. And that means that measuring the spectrum of the microwave background, you can really open a new window to the early universe and test, energy release processes and non-equilibrium processes throughout the history of the universe. Putting the mu and y-type distortion into context, this is the picture that we arrive at. So in the early phases, we have the mu-type distortion and the y-type distortion with these simple estimates telling you what the mu parameter and y parameter would be if you just think of the energy that is being added to the microwave background. And then, of course, you also have the very efficient thermalization era where you basically can ingest any of the energy that you would be releasing and just change the temperature of the microwave background. But the signals that we can really study are the mu and y-type distortion signals. However, this picture has recently been refined. We now understand that this transition between the mu era and the y era is not actually instantaneous, but we have this hybrid era where we basically get an interpolation between the two extremes. And the interesting thing is that this contains new time information, time-dependent information that adds another dimension to the problem, which allows us to, in principle, map time-dependent processes through this era. And if you add as well the details of the hydrogen and helium recombination process, then you have another way of really timing energy release processes. So this is not just a simple one-number integral constraint that you could imagine doing by very high precision measurements, but you can actually go in much more detail, extracting some time-dependent or scale-dependent information. And I just want to highlight this a bit more, because of course, if I just think about the three fundamental spectral distortion shapes and the sum of these spectral distortion shapes, then things would be very boring if this was really the signals that are created at these intermediate areas, if they were just the sum of these three cases. And it is indeed true that these signals created at injections, single injections at other redshifts, they basically create this interpolating signal. And if you compare the different shapes, then you have this additional information that can be used to really extract time-independent processes. And here's the explicit demonstration that what I'm saying is not just made up. If we just take those signals that I just showed you and subtract the best fitting mu plus t temperature plus y parameterization, we can actually see that there is a departure, that there is a signal that we cannot model, and that is the time-dependent residual distortion signal. It's a non-mu, non-y contribution to the signal that we can really use to do time-dependent measurements. Okay, so this is the state of our global picture of understanding how thermalization processes evolve when you have energy release. But and we can calculate these kind of things now very, very accurately with the code Cosmotherm. It's a code that I've written many years ago already, and it is for a long time overdue. Should be released. We are hoping that we will put it out by the end of this year. But anybody who really wants to use this code, I'm happy to share it with anyone. Just drop me an email. The important thing is it has many energy release processes already implemented, so one can really calculate and predict for different models the signals that one would be expecting. We model, or we have the opportunity to actually model the Comptonization process, the double Compton process, and Bremsstrahlung processes very accurately, even using full kernel treatment. So you can really test for the precision of the calculation. Of course, the calculation becomes more expensive when you do a kernel treatment, but this is capabilities that were added with my team here at Manchester. Over the past recent years, Boris Bollier and Andrea Ravenni and Sandeep Acharya. And we also are able to solve photon injection problems. In contrast to just energy release processes, you can have photon injection, and depending on where the photon is injected and when, you get different signals. And the signal richness is actually much, much bigger than just these simple thermalization distortions from energy release that I showed as an illustration before. So this is also possible now and can be calculated in detail. I want to show you an explicit example for a decaying particle, where I chose the redshift of the decay, or the lifetime equivalent redshift of the lifetime, to be 8 times 10 to the 4. This should be a signal that will be somewhere between a mu and y-type distortion. I assumed an energy release, total energy release of 6 times 10 to minus 6. This is not ruled out by Firas. I'm starting at high redshifts. This is a snapshot at the end, but let me start this movie. I'm showing here in the upper panel the basically distortion signal, and then in the lower panel it is the effective temperature as a function of frequency. Here's the computational frequency, so h nu over kt. Of course, in terms of real frequency, this can be mapped into gigahertz, for example, at the 2 times 10 to minus 2 level. And the channels that are normally being used in CMB observations, also with CMB spectrometers, they are in the upper part of the right part of this panel. So let me start this distortion calculation. I'm assuming that initially I have no distortion, but as you can tell, there is even well before the redshift of the real injection, which is, I'm showing here 10 to the 6, there is already a distortion created. And this distortion comes from the cooling process that I mentioned before. But now we have here the injection happening, and you see how the distortion slowly builds up. So you get an increasing dip in the temperature, which is around a gigahertz or so, and you get this buildup at high frequencies. And then as you go through the thermalization process, you see how the distortion, in particular in terms of the temperature shape, achieves a quite complicated or a more interesting shape, which is precisely this time-dependent information, because the classical mu-type and y-type distortions they look quite different in this metric. And then at the very late times, you even see this low frequency absorption, which comes precisely again from the cooling of baryons, because they decouple at redshift of roughly 200 from the photons and then lead to a cooling process. So this is the global picture where you have the interplay between cooling because of the adiabatic cooling and then the injection of energy from the decaying particle. We are also with Cosmotherm able to calculate large distortion signals. So now I'm not showing the difference, the real distortion, but I'm showing the total spectrum here in the upper panel. And here again, the distortion. I'm now starting at slightly later redshifts, but I just cranked up basically the energy release process, how much energy was released. And you can see how you create this initially mu-type shape. And then as time goes on, you see now explicitly this distortion appear, and I needed to do a real nonlinear calculation here because the distortion is actually not a small distortion, but we can treat this in detail now and really capture all the dynamics of the system. And you see an increment at high frequencies, and you can even see at very low frequency again an increment, because the average electron temperature is actually higher than the black body temperature in this distorted radiation field. So all that dynamic can be calculated and taken into account, and we have even shown that distortions with large distortions, they have a different thermalization rate than small distortions, and this is actually something that is potentially relevant at high redshifts. So in the very early phases, deep into the thermalization era, where the temperature shift is mainly produced. Okay, so and then finally, I want to mention we are now able to calculate these distortions even more efficiently, because we found a new discretization of the distortion Green's function, which only requires basically solving 18 parameters for describing quite accurately the distortion shapes. This is work that I did with Andrea Ravenni and Tom Kite. And just to highlight, the previous calculation was I took the video in real time. If I switch off the video, it will take like a couple of, like maybe 10 seconds, 30 seconds to do one of these thermalization calculations. So it's not actually that slow, but with this, you can basically do it in sub-seconds, can do the calculation. And that is a really interesting new avenue, because it allowed us to also solve a real photon Boltzmann hierarchy in terms of spectral spatial evolution of the CMB. So not only looking at temperature parameters, which is, for those that are familiar with the perturbation equations, this is basically the evolution equations for the temperature parameters. If you just think here of this y vector replaced with the temperature anisotropy, but when you add spectral degrees of freedom, you can actually augment this hierarchy and basically solve now 18 plus the temperature anisotropy parameters, and then get power spectra of this, which is, here's just an example for single energy release scenarios where you have an injection at some given redshift, and you're then following the thermalization process and all the propagation of the modes, and you can see how you can create temperature and mu anisotropy correlations, and temperature and y anisotropy correlations, and also residual distortion correlations, which are giving you information about the time dependence of the process, when, how much energy was there, and so on. And these can all now be calculated. And the really cool thing is that this is signals that you can actually study with CMB anisotropy measurements. You can literally look with Planck, and we have even constraints on these kind of processes from Planck explicitly. You can also in the future look with Lightbird, CMB stage 4, and maybe even futuristic experiments like PICO, of course, the Simons Observatory. And as we have recently shown, actually today, the paper came out, the SKA even can help contributing to this, science case. And I think David Zegier is also going to be talking about this in more detail in one of the contributions. So this is really exciting, and that summarizes in some sense where we stand with our understanding of spectral distortion theory. And I think there's lots of opportunities there. But now let me go back to the observational frontier and what we can actually learn from spectral distortions. So here, again, this figure that I showed earlier, and these mu and y parameters. The important thing is that these parameters, they are very small, and that means that we have already excluded large energy release, at least in the late phases of the universe. So why am I really talking here? Because I mean, this looks like this is all ruled out, and there's nothing interesting. It turns out that there's lots of signals that could be in principle created, and there's also guaranteed signals that are certainly expected, and these signals are actually just below the virus limits in some sense. So think of this figure again as a redshift dependent, time dependent information. The signal strength is the y-axis, and then here I even just for guidance I've looked at I'm giving here some mission concepts. So virus is up here, and Bisou, Pristine, Pixie, Super Pixie, and Voyage 2050. I will mention these in a second as well. They have varying sensitivity essentially. So virus didn't have the sensitivity to, for example, look at the late time signal created by clusters of galaxies on the average, or the relativistic correction that comes from this. It also didn't, was far away from being able to look at the damping of acoustic modes, which predict a mu distortion of 10 to minus 8, and then the adiabatic cooling process that I already mentioned, and the cosmological recombination lines. But futuristic experiments might be able to reach down to this sensitivity. And then these are just the guaranteed distortions, but there's also all these non-standard processes. And, as you see, there's many things that are being mentioned that actually are being debated and talked about quite actively in the community. For example, axions, primordial black holes, primordial magnetic fields, small-scale enhancement of power. All these things could be happening and could be, seen or constrained with spectral distortions. So spectral distortions really open a huge parameter space and a discovery space as well. And any step over virus would be a massive improvement. So here's the Lambda CDM distortion signal predictions with the late time distortion from the late universe, the y parameter of order 2 times 10 to minus 6. Then there's a relativistic correction to the signal. I will get back to that in a second. Then there's the mu distortion from the damping of acoustic modes at small scales. I will also go into more detail there. Which, as you can see, these signals are, within reach of the Pixie sensitivity. However, here, foreground marginalization was not yet taken into account, so it is actually not so easy to get to the mu distortion from acoustic damping. And then there's the recombination lines and also this adiabatic cooling effect. So let me go into more details about that in a bit. I want to show this one slide that summarizes some of the activities that have been with respect to CMB spectral distortions. And I want to highlight, of course, that the state of the art is unfortunately still COBE virus. We have made some attempts from ground and also with the balloon to improve the limits from COBE virus. However, in total, one could probably state that COBE virus is really still the state of the art in terms of measurements. However, it is possible experimentally, since the proposal of the Pixie proposal in 2011, it is actually possible to improve the limits in principle of COBE virus by a factor of 1,000, possibly even with more futuristic experiments a factor of 10,000, and that opens the door to measure actually signals. However, all these activities, Pixie, Prism, Pixie again, or another version of Pixie, Super Pixie, and so on. These are all only proposals, and the community, I have to say, the community has really missed out on the opportunity to really push this frontier since basically 30 years, because in CMB anisotropies, we have seen the anisotropies, and we have seen a lot of really exciting results, and there's of course the great perspectives with B modes and high order statistics and all these kind of really exciting aspects. But CMB spectral distortions are really still in the dormant state basically since COBE virus. And I think it is really important that we get the ball rolling on this again. And it is really exciting to mention these experiments down here, which are indeed some process of moving forward in the topic. So Apsara is going to look at the recombination lines at low frequencies from the ground. Cosmo is an Italian-led experiment with Paolo De Bernardis and Silvia Masi and Elia Battistelli pushing for this to measure from Dome C. And then Bizou, a French-led Bruno Maffei and Nabila Aghanim are the main leads of this experiment that is targeting the spectral distortions from a balloon. And then TMS, the Tenerife microspectrometer with Jose Alberto Rubino Martin pushing for this, which is going to be mapping or looking for the absolute measurement at 10 to 20 gigahertz. So this is not just fiction anymore, and I want to show this. Cosmo, there's indeed progress in making progress in terms of here's Kralstad, Elia Battistelli, and Silvia Masi, one can make out her feet, working on this. I was visiting the lab, actually, I think it's 2 years ago, where I was shown, for example, the modulator for the Fourier transform spectrometer. I was extremely happy to see all this, components there. And it's basically now just a question of shipping the instrument basically to Dome C to start taking observations and calibration and so on. So this is really really going forward. And then Bizou, we are expecting an official announcement of Bizou being chosen to go to phase A later this summer. So this is meaning that Bizou, in principle, could be measuring spectral distortions from a balloon in a timescale of 5 years from now. So by the end of 2020, in 2029 or so, we will be hopefully having some first measurements which are improving over COVID virus, probably at the level of a factor of 20 to 50. So this is really great. And then there's also the very exciting opportunity that has been highlighted by the ESA Voyage 2050 report that CMB Spectral Distortions are a recognized probe of the early universe physics. And this is really, really great news, because it means that we just have to, organize the community, get together, come up with a great and credible proposal, and then hopefully we'll be able to, measure these signals and learn something about the early universe. But it is really time to get organized now, because space missions take a long time, and we although the CMB community in particular is very actively busy with the B modes, we really need to try to dedicate some time to spectral distortions as well. And activities like TMS and Cosmo and Bizou are really crucial for this process. So I think this is all extremely exciting developments that we are seeing currently. Okay. So let me talk about the Lambda CDM distortion signals first. I already mentioned the relativistic correction signal and also the basically average sky Y distortion, just coming from the cumulative flux, if you will, from clusters of galaxies and all the hot gas in the universe. Because this gas is not because it's actually pretty hot gas, you get a relativistic correction to this signal, which comes from the fact that you have basically temperatures that lead to electron velocities that are a fair fraction of the speed of light, and you cannot just calculate the distortion in the non-relativistic limit, which is the classical Sunyaev-Seltovich effect. So you see this correction to it, and that will allow you to probe not only the average pressure of the universe, but also the temperature of the universe. And here's this, highlighted in a nice figure that just shows you the range of the parameter space that is currently covered by different simulations. And what a PIXI, or here Pristine as another experiment that was proposed to ESA, how they could tighten these limits incredibly. So we would really learn about feedback processes and the structure formation process using these distortion signals. Okay, let me come to the dissipation of acoustic modes, which I think is one of the key and really important signals to understand and how they come from. And this is also the key driver for the mentioning of spectral distortions as a strong contender for a probe of the early universe. And it is nothing else than just the dissipation of, as I said, small-scale acoustic modes. So perturbations in the universe that are basically being dissipated and lead to energy release. So let's look at this in detail. So here's the CMB anisotropies again, and we have measured with Planck, ACT, and SPT, and many other experiments. We have measured the power spectrum down to very small scales, and you see there's this, damping of the acoustic modes by silk damping, which leads to this, quasi-exponential decay at small scales. If we were able to undo this damping process by basically just switching off corresponding terms in our Boltzmann equations, this is from a paper by Wayne Hu and Martin White, where this is just illustrated. We would be expecting fluctuations that have Doppler peaks, but they would be basically unimpeded. And the erasing these anisotropies is precisely what causes energy release. So that leads to distortions of the microwave background, and the ideas go back to the 1970s by Sunyaev and Soldovich. And the physics is very simple, because if you just imagine you have a box with black bodies, one black body part being a little bit colder and a little bit hotter. Here's the spectrum of the hotter part, and here's the colder. If you take the average temperature black body, that would be the black line. And if you now take this box and you shake it to make it one uniform distribution, so you have here your spatially uniform distribution, but because you're just shaking it and you're just mixing the photons, which is, by the way, done by Thomson scattering, which leads to the silk damping, you're not changing the real energy distribution. So it's like taking the sum of two black body spectra with different temperatures. And of course, that means there's not a black body again. And then this is equivalent to a Y distortion at high frequencies, and that leads to the thermalization then through mu through Y to mu distortions. That is what is happening basically in the early universe at small scales. And this process was already used back in the days by Kobe-Firas, in fact, or with Kobe-Firas data to constrain the spectral index of scalar perturbations. This is work by Wayne Hu, Douglas Scott, and Joe Silk, where they say, knowing the anchor that they had at large scales from Kobe DMR, they could basically say, well, given the level here, if we allow a power spectrum, this power spectrum slope cannot be much larger than 1.6, which is, just precisely using this dissipation of acoustic modes as a constraint. The calculations were based on old estimates of the dissipation rates and things like that, but it was still a very, very interesting combination of anisotropy information and spectrometer. We can calculate the signal now very accurately with Cosmotherm, and this is the prediction. You would see a Y parameter of a few times 10 to minus 9 and a mu parameter of 2 times 10 to minus 8. There is also a residual distortion, but that is a smaller contribution. So this is a signal that is created continuously due to the energy release. And it is with Pixie, unfortunately, just below the standard version of Pixie, just below the detection limit because of foreground marginalization. However, we can come up with better implementations of Pixie or multiplications of Pixie that in principle can reach to this level and extract the signal. Okay, so what do we learn? Well, the distortion signals are really created by modes that are, way beyond those that we measured with the CMB anisotropies. So here's, the constraints we have directly from CMB anisotropies, and then at smaller scales down to, a few times 10 to the 4 inverse megaparsecs. That's where the spectral distortion constraints come in. This is here the mu distortion constraint, and then here at larger scales you have the Y distortion constraint. And there's also a constraint coming from reheating, that you're thermalizing and producing basically an increase in the temperature, and that also is excluded or constrained by BBN limits. So it is really important to highlight that in principle, Firas has ruled out that supermassive black holes could be just created from horizon scale collapse of density perturbations, at least in the limit of Gaussian fluctuations. So this is a really, really strong implication of these measurements. And with Pixie, one could go down to almost reach the level of the expected scale invariant power spectrum. Then there's of course all these other probes of scalar perturbations, and one can of course ask the question, if, for example, there is a signal that is indicative of large amplitude fluctuations here, then how do you get there? And that process of reaching from these scales to the smaller scales, it cannot be happening arbitrarily quickly, and that means you can always expect to have a complementary information from the CMB spectral distortions. So this means that CMB spectral distortions will actually help shedding light on, for example, questions of primordial black hole formation or the enhancement of small-scale power in general, which is a really, really important scientific ingredient. And one can similarly ask the question what spectral distortions do for gravitational wave backgrounds. So if you say there's a gravitational wave background, then if you have modes that are here in this range of frequencies, fairly large, low frequency modes, they could in principle directly dissipate. They could in principle directly dissipate and create spectral distortions. However, these signals, because coupling to gravitational waves is not very efficient, will not be very large, and therefore this is fairly weak limits. With PIXI, you could improve this strongly, and in the Voyage 2050 direct measurements from the dissipation from tensors, you could again improve. And you can see that there's even the possibility to close some of the holes that are still existing from pulsar timing measurements, expected pulsar timing measurements, and then large-scale B-mode surveys like here for LightBird. And then there's also the interesting scalar-induced gravitational waves, which we have been hearing a lot about with respect to the nanograph measurements. And the important thing is that in principle, the current measurements do not exclude that LightBird could have a significant contribution of scalar-induced gravitational waves. However, with PIXI, you could completely eliminate that possibility. And it just comes from the fact that it eliminates enhancement of power at the scales of 10 to the 4 inverse megaparsec. So this is really an important application of the spectral distortions, in addition to what I said before, because it can actually ask the question, what is the origin of, rule out the origin of B modes, large-scale B modes being related to scalar-induced gravitational waves. So this is really exciting. Okay, let me come to the recombination lines, which is one of the topics that I've been working on many years, also with respect to the analysis of Planck data to get the recombination history right. And here is the signal that you get. This signal is quite small. It's much smaller than the mu distortion, but it has many, many features because of the dynamics, and the different lines that are active during the recombination era. And therefore, this signal, if you actually measure the mu distortion signal, you will also see the recombination lines, because it's only a factor of 6 below. But for the after foreground marginalization, you lose almost an order of magnitude in terms of sensitivity to the mu distortion, and that brings you down to basically to the recombination lines, the necessity to go as deep as the recombination lines. So this is a signal that we can in principle target, and it tells us about various phases in the recombination process. So the hydrogen lines, they come from redshift 1400. 260,000 years after the Big Bang. Then we have the helium-1 lines, which are around 130,000 years, and then helium lines 18,000 years after the Big Bang. If something non-standard happens between these different recombination eras, you could expect this to be reflected in the signals that we see. And here I just show you a figure from an old paper that I wrote on energy release from dark matter annihilations, where you basically change the recombination dynamics and see how that changes the recombination lines. It's just to prove to you that there's actually effects that you can see, and this is something that we can actually study to look at the presence of these kind of perturbations. I want to quickly mention the Hubble tension, which is, of course, a very exciting topic that people have heard about. And from the HNUT Olympics, early dark energy, primordial magnetic fields, and varying electron mass models have been actually found to be the best solutions or good candidate solutions. And this is, of course, really exciting, but you have to ask the question, how can you distinguish the possible solutions? And the recombination lines are one way of doing this, which is a paper that Luke Hart and myself have written now a couple of years ago, where we showed that, for example, early dark energy models modify the recombination lines in a way that could be, in principle, indicative of this process. In a similar way, varying fundamental constants, they have effects on the recombination lines that could be leading to understanding this dynamics. And this means that you can actually probe this process, and you could even talk about models that have that are basically the scalar field is also responsible for changing the electron mass. So there's many things you can do, and promoting magnetic fields can in principle also directly change these recombination lines. And this is something that I'm illustrating here in this figure, where I just took the density induced fluctuations that you would have in the recombination spectrum, where you have here some slightly overdense regions and some underdense regions. And if you take the ensemble average of this, you can actually see that the lines are, obtained in different models are departing from each other again. And by measuring finely and the position and the shapes of these recombination lines, you can actually distinguish this. And the simple fact is only that it's basically coming from the fact that you have nonlinear corrections to the spectral shape, and you cannot just say, well, the average of the recombination lines is the same as the recombination lines of the average parameters. And this is an opportunity that allows us to maybe even test the origin of this Hubble tension. Okay, so in the last 5 minutes, I'm going to say a few words about the link of spectral distortions with 21 centimeter cosmology, which I think is extremely important. We all heard about the edges result. And of course, there's a big debate. What is the meaning of this result? But one of the interpretations that was immediately looked at is that you can, in principle, ask about how to alter basically the ratio of the radiation temperature to the spin temperature. So one possibility is extra cooling. If you want to make the absorption signal much stronger, you can cool the baryons and in principle make that signal much more negative. Or you could have an excess low frequency background. This first idea reminded me of a spectral distortion calculation we did with Yassin Ali-Hamoud and Mark Minkowski, where we actually looked at how the extraction of couplings with dark matter could be in principle leading to negative chemical potential distortions, and thereby be constrained with Kobe-Firas again, and also Pixie in the future, which is, in a sense, very similar to this idea of extra cooling, but this was at earlier times. Nevertheless, let me come to the low frequency excess. We know about this low frequency excess arcade measurement since many years now, and in recent years there was even a proof that the measurements that arcade made at the higher frequencies are really what the extrapolation from these measurements down to the 150 megahertz regime is giving you actually a consistent picture. So this excess is real, and nobody really understands where it comes from. People have tried to say, well, this is just the population of radio sources, let's stack all the radio sources we know, and you fall a factor of 5 short. So there is no simple explanation. Another suggestion was maybe it is related to photon injection distortions and Comptonization, but all these kind of models are having difficulties. Accretion models is another way. So what is the origin of this signal? We considered a cosmic string solution to this arcade excess, where we did a detailed calculation of the evolution of cosmic string networks and then thermalized things, and basically obtained this plot on the constraints of the cosmic string tension versus the current that these superconducting cosmic strings could have. And it turns out that this regime here is ruled out, and in the future Pixie could improve even more. But there is currently still this one solution that's possible, that in principle could be solving this radio background, and it is consistent with all the data that we included. And how does this work? Well, this is how it looks. It goes through the data points in a very similar manner as the best fitting Bauer laws would be matching the data. And this is the parameters that we are suggesting. This is not to really say these are the parameters that there are, because there's lots of details in the modeling of cosmic strings, but it's just to say that if you have actually continuous photon injection, you will be seeing this radio excess if it is in injection also at low frequency, be really related to this. And the exciting thing is that this is in principle a target also for CMB spectrometers like TMS, BZoo, and Pixie could be basically asking the question how the signal is at high frequencies, and thereby potentially even distinguish different origin. One important thing I want to highlight, but I don't have time to go into details here, is that this, of course, is now interplaying with the the 21 centimeter line, just like this original suggestion of this radio excess potentially limiting the line. And you have to take into account soft photon heating processes to actually get this really sorted. So this is really intriguing, and it just shows that there's lots more to be learned from CMB spectrometers, and I think this is very exciting. Another way to probe this is the so-called radio Z effect, basically the scattering. Instead of just saying there is a processing of the CMB, you also can look at the processing of the radio background, and this would be leading to basically signals that could be looked at in the radio, for example, with Meerkat, LOFA, and the SKA, but I do not have time to really go into this. So let me wrap up. I hope that I convinced you that spectral distortions are a really exciting, new frontier, and that there's lots of things we can learn from them, with guaranteed signals waiting for us, but also non-standard new things that we could look at. It has a huge discovery potential and also is complementary in many, many ways to other probes, and things like Cosmo, TMS, BZoo, and maybe something in the future from space in the Voyage 2050 program would be really exciting. I mentioned the synergy with this 21 centimeter, where basically understanding the processing of the 21 centimeter line might require us also understanding the higher frequency tail and the dynamics and the coupling of this spectral distortions. I didn't have any time to look at synergies related to CMB to the cosmic line intensity mapping, but here's a paper that I wrote recently together with folks from CETA that highlights this opportunity. And then I mentioned briefly the opportunities with CMB anisotropies and spectral distortions, which can be targeted by LightBird, CMB stage 4, and even PICO and other experiments, and potentially even SKA. So I hope this convinced you that this is really exciting. Thank you.